All right, so now we have learned about the structure of multi-layer perceptron or its architecture. Now let's see how it calculates the output if we give an input to MLP, right? So basically we want to see how to compute the output. Um, oh, so this is to compute the output given that we have an input. So our input xi, it belongs to the dimensional input, and we want to be able to calculate the output. Now, to do this, we only go forward from the input layer towards the output layer. And this is called a forward propagation. So we are going to have a forward propagation, and we are basically, you are going to see that we have other phases, but this is called a feed forward phase. All right. So what we have is that because it's a two-layer network, we are going to first compute the values in the hidden layer from the input layer. So here, right now, we are assuming that we have all the W, I, J, H, and O's. So we have all the weights, and we want to just compute the value of the output layer for our input, right? So first, we are going to compute the values in the hidden layer. So what are our hidden layers? So first we are going to compute, what color was it? Blue. So we are going to compute ZJs in the hidden layer. And from there, we are going to compute OK, for example, from the output layer. Now, to compute the ZJs is similar to the previous ones that we have seen. We have to calculate the net J first, and then we have to apply the activation function on net J. You remember that it was a two-step process, right? So for ZJ, when we have just one hidden layer, we are going to first do this calculation of net J, which is, and we have seen it was, it was Bj plus the summation of Wij. Now, this Wij is between the input and the hidden layer, so Wijh multiplied by xi, each of the xi's that we have for all the dimensions, I equals to 1 to d, and then the augmentation or bias is taken care of with bj. It's also have an h. And then we are going to apply f, the activation function of the hidden layer, let's call it fh, on net j. Now, this activation function, it can be any of the activation functions that we have seen. It can be sigmoid, it can be ReLU, it can be any activation function that we choose for the architecture. So each layer is going to have a different, it can have a different activation function. Now, if I put all of the neurons in the hidden layer together as a vector, I will have what? I will have a vector z, which is basically z1, z2 until zm transpose, right? And z0 is the augmentation, so it's always 1. So basically, I can say the first step, my net in the hidden layer is a vector that is putting together all the net 1, net 2 until net m, right? My vector of net is going to be equal to my BH vector, actually BH vector, plus my W, oh, it's a subscript, so BH, plus my WH matrix transpose multiplied by the input vector x. And then in the second step, when I apply the the activation function, then I'm going to have my z, which is the value for the hidden layer, is equal to applying my activation function f of h over my net h vector. Okay, so this application of f is an element-wise application of f, meaning that I am applying f of h on all elements of net h vector. So it's basically equal to a vector that is fh of net 1 comma fh of net 2, etc. fh of net transpose. So, okay, so what we have done so far is that we have calculated the values so far from the input to the hidden layer. So this is z, this is x, and we have calculated this part, WH, BH. Now, what is the next step? Well, the next step is to move forward to the output layer and calculate the values there, right? So for the output layer, our output layer, we have WO, we have BO, and then we have the output layer, right? So calculating the output layer values from the hidden layer is very similar to calculating the hidden layer values from the input layer. So just, I will write a summarization. What we are going to have is similar. We are going to calculate a net value for all of the neurons in the output layer, and then we apply the activation function in the output layer on them. So we are going to have net of output layer, the vector, is equal to the bias of output layer weight plus the matrix WO that has all the weights of edges between the hidden and output layers transpose multiplied by z, vector z this time. So it's as if the input for our output layer is the values from the hidden layer, right? So the input for each layer is the output from the last layer. That is how feed-forward networks like MLP work. So that is calculating the net, and then we are going to calculate the actual values of O, the output values, which is going to be applying our activation function f of O or on the net values, net O values. So this f of O can be different from f of h. Okay, so you can have a different activation function for each layer. This is how, when you have an input data point, you are going to calculate the output data point for it. So what we do in here is that when we have a large data set with n data points in it, we are going to give our data points to the network structure one by one. So we are going to first give the vector, we are going to first give x1 to the network and calculate O1. We are going to give x2 and calculate O2, etc., until we are going to give xn and calculate O n, or output n, for our data point. So just mind it that we are dealing with the data points one by one in these kinds of setups. Now, this forward phase, or forward propagation, is for calculating the output from the input if we have the weights, right? But we need to be able to learn the weights also. How do we learn the weights? Well, we train the neural network using our training data set to